Afternoon, and welcome to our course in number theory. We're going to be using this textbook by George Andrews. Let's see right there. This is a elementary introduction to number theory in that it does not use anything like abstract algebra or calculus or anything like that. It just uses the basic tools of number theory. This is the first video in our series, and we are going to discuss a useful tool for proofs in this class, and that is mathematical induction. So let's switch over to the document camera and give some examples. So the technique of mathematical induction is actually used to prove classes of statements, as long as those statements involve the natural numbers. So let's start with an example. So this is our claim. The claim is that for any natural number n, if I take this sum, 1 plus 2 plus 3 plus 4, and then I keep on going until I hit my natural number n, that will be equal to n times n plus 1 divided by 2. So I thought I would look at a few specific examples of that claim. So this one I've got written right here is the claim for when n equals 5. 1 plus 2 plus 3 plus 4 plus 5 is supposed to be equal to 5 times 5 plus 1 divided by 2. Okay, and we can see this side, if we add them up, 1, 3, 6, 10, 15. And if we look at the right-hand side, 5 times 6 is 30, divided by 2 is 15. Okay, so the claim is true for n equals 5. A couple of other examples would be something like this. For n equals 3, the claim is saying that sum should be equal to this. And for n equals 1, the claim is saying the sum on the right, which is just one single term, should be equal to that. Okay, now we can see by direct computation that all of these statements are true. But of course that does not prove our claim, because the claim said for any natural number n, this relationship would hold. So in order to prove that, we're going to need to use mathematical induction. So when you're using mathematical induction, you always start with your base case. Okay, now typically it'll be when n equals 1, though that might not always be true. You might need to use a different starting value, but in this case 1 will work. So when n equals 1, the claim is saying that this equation should be true. Okay, so if we look at the right-hand side, I've got 1 times 2 divided by 2. So this is saying 1 equals 1, so that is true. Okay, so the base case is almost always a trivial computation. Now, our next step is to look at the inductive hypothesis. Now, for this particular problem, it's going to be that we are assuming that for some fixed natural number, that this equation is true. Okay. Now, the inductive hypothesis has to be done using a generic natural number. Okay, now, this is the key part of any induction proof. The key part here is the induction step. okay, we're going to consider this expression right here, 1 plus 2 plus 3 plus dot 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 plus k plus 1. Okay, now the induction hypothesis says that I can take the first k terms and replace them with k times k plus 1 divided by 2. Okay, so by the induction hypothesis, this first group can be replaced by k times k plus 1 divided by 2. And now I want to see what I can do with this expression. All right, now I know what my target is. Okay, I'm going to leave myself a blank line here. My target should be k plus 1 times k plus 1 divided by 2. All right, that's my goal. I want to make this look like this if I can. All right. Well, up here I can see, all right, both of these terms have a factor of k plus 1, so I can factor that out. And what would I be left with? Here I'd be left with a k over 2. And over here I factored out everything, so I'd be left with a 1. Now, if I were to combine fractions inside these brackets, well, I need to get an LCD. And my LCD would be 2. I'd have to rewrite this as 2 over 2. And then once I've done that, I could combine the numerators to get k plus 2 over 2, and that is in fact equal to this. Okay. And that actually completes our proof by induction. Now, there are some notes I want to give you here. Okay, so you might think of an induction proof as showing you can knock down any number of dominoes that you want. So in your base case, you're showing that you can knock down the first domino. The induction hypothesis shows that whenever actually, I guess it's the induction step, really. The induction step shows that whenever any domino falls, the next one also falls. Okay, so when we do the induction hypothesis, we're assuming that a domino will fall. And the induction step shows that if that domino does fall, then the next domino will also fall. So these two together show that all the dominoes will fall, because if the first domino falls, and whenever any domino falls, the next one falls, that means we are sure that domino number 2 will fall. And since we're sure that domino number 2 will fall, and whenever any domino falls, the next one also falls, that means domino number 3 goes down. And since domino number 3 goes down, the fourth one goes down, and so on down the line. Okay, so that's a pretty simple example of an induction proof. Let me go and look at a slightly different one, a little more complicated, but not that bad. So what we have here is our claim. And the claim is that when I add up this series of fractions of this form, 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4, and then we keep on going in that way to 1 over n times n plus 1. That should be the same as n over n plus 1. Okay, so remember, it's a whole series of claims, really, because we're claiming this holds for any natural number n. Okay, so our proof, of course, is going to be by induction. So we look at our base case, and we can do n equals 1 here. So when n equals 1, it says that the first term on the left should be equal to 1 over 1 plus 1. Okay, this is, if I think of this when n equals 1, we just take one term over here, and I'd replace n equals 1, n with 1 over here on the right. Here I get 1 over 2, I get 1 over 2 on the right-hand side, so that is true. Now, our inductive hypothesis is to suppose that for some natural number k, that this expression is equal to k over k plus 1. Okay, so we're going to assume that for some natural number k, this expression is equal to this one over here. And now for the induction step. So what we need to do is we need to consider what happens when we look at this sum. All right, now you'll notice that there is always a relationship between the inductive hypothesis and the induction step. Okay, your induction step, you're taking the left-hand side of your inductive hypothesis and you are adding the next term. All right, now the inductive hypothesis says that this bunch of terms can be replaced by k over k plus 1. Okay, now it doesn't say anything about what happens when we throw this into the mix. So we have to look at what happens. All right, well, we're adding two fractions here. So we've got to get a common denominator if we're going to add these fractions. So the common denominator would be k plus 1 times k plus 2. So we're going to multiply that first thing top and bottom by k plus 2 in order to get it in terms of our common denominator. Now that we have the fractions in terms of common denominators, I can combine the numerators. Notice I multiplied through the k there. All right, one more step. I noticed that numerator factors, it's actually k plus 1 squared. And of course, I can cancel a factor of k plus 1, and I'm left with this. Now, I want you to look here. if I had n equals k plus 1, if I replaced n with k plus 1, this would be a k plus 1 and a k plus 2. And this would be a k plus 1 over k plus 1 plus 1, in other words, k plus 2. So the claim for n equals k plus 1 says that that sum that we started with right here should be equal to k plus 1 over k plus 2. And if the inductive hypothesis holds, then that part of the claim is true. And since we've shown that the base case holds, we have shown that our claim will hold for all natural numbers n. Okay, so two examples using the technique of mathematical induction. It's a very useful technique of proof when you are working with claims about all natural numbers. So in other words, if you have a claim that says, okay, for all natural numbers n, 1 cubed plus 2 cubed plus 3 cubed, dot, 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 all the way up to n cubed is equal to something, then you should try to prove that by mathematical induction. So remember, the three parts are the base case, the inductive hypothesis, and the induction step. Now, the most common error that I see is jumping the gun on the induction step. Okay, so you have to write out the claim, the left-hand side, when n equals k plus 1. Then you have to use the inductive hypothesis and then go from there. Okay, you can't just write down both sides. That's writing the conclusion. You can't start with the conclusion in any logical argument. You have to start with the premise and then work your way to the conclusion. Okay, so you got your base case, your inductive hypothesis, your induction step, and that's how you work through a proof by mathematical induction. So very useful. In our next video, we will talk about using the technique of mathematical induction to prove claims about properties of the Fibonacci numbers.